So welcome to our second class, which is your third class of this semester. Again, if you recall the first time we met, right? I gave you guys basically an introduction to the AI concept, okay? I went to a great length trying to clarify a lot of maybe misconception about what AI is all about, what application of AI is all about, and basically lay the groundwork for the rest of the semester, okay? Let me ask you this, just curious. Let's say we gave you, again, don't worry about taking note anything right now. Just imagine that you knew about this course called AppliedAI, okay? And you haven't seen the syllabus, you haven't seen the class schedule. What do you think the class schedule would look like? Okay? So one of the way the class schedule could look like would be something along the line of, maybe a bit smaller. Okay, right? So obviously you have, oops, it's not brush, but it's a pen, right? And okay, color, okay. So obviously you have a work week of first week of intro, right? And then the second week all the way to the end could be something like AI in medicine or whatever, okay? AI in manufacturing, okay? And all that, right? This would also make sense, right? Apply AI. How do you apply in various things? Problem with that is, number one, I can't cover all the application area. That's not so bad because sometimes you run into a new application area and you recognize, well, some of the techniques and challenges are similar. So you can apply what you learn. So you do your own extrapolation, generalization. Okay, that's fine. Thing is though, it's also a little bit unimaginative because after all, you're in a disruption age. So you have no idea what kind of strange application area you might end up in. Okay, even right now, the universe of application is quite vast. So to cover in at most 10 items, that's not going to do it. So the way, just to confirm, we've done it is we designed it along a different line, right? Let's see, we got this very fast. Okay, so there's intro, but then we sort of like split the thing into two tracks. One is how AI works, right? And the other one is how to work with AI. Okay, and we kind of like, so the first one is not exclusive, but the first one roughly is kind of like my part of the lecture, whereas the second part is leans more heavily toward Marcos, although there's a lot of overlap and all that. And then we kind of like alternate back and forth a little bit. The way this works is you get an insight of how the tools work. Okay, you get the insight of how the tool works. It doesn't really matter if it's 5 years from now or 20 years from now, or AI may be outmoded, maybe reinvented, maybe a new wave of AI, new wave of innovation area. The idea of scrutinizing the toolkit for what it is, understanding how the toolkit doesn't work, the limitation, the rationale, the inner logic, right? It's going to stay with you. Okay. But it's not going to stay with you long if all you do is listen to me tell you a story about how AI works, if you don't get your hands dirty. So there's a lot of experiential learning that comes with that. Okay, it's one of those things where in neuroscience it's confirmed that you kind of learn in multi-mode. So you listen, but you also practice, and then you learn from mistake on that stuff. Right. So in line with that, okay, I want you to, for the first half an hour or so, okay, not worry about taking notes, but try to think of yourself as an assembly of thinkers, okay? I'm just going to ask you some idea that's supposed to provoke your thoughts. That's going to lead to our more intimate understanding of what is it we after, okay? What is it we after in the AI frontier research and whatnot? Okay, so let me ask you this. Okay? Imagine if I were to ask you to construct, okay, or to be in a company that creates a perfect humanoid AI. Okay, humanoid AI, right? It's gonna comprise of various capabilities, some hardware, some software, some programming, some coding. Okay, but you're now going to organize your company along lines of competency that the AI has to have, or development, or factory, or R&D. Okay. Now, I want you to have an open mind, but at the same time, I kind of like we'll sort of like walk you through rather than leave everything up and open. So I maintain that, okay, and just follow with my thinking with this. There are actually there are actually 5 different areas, okay, that are kind of like aggregated together into what it takes to make a perfect humanoid android AI. 5 capabilities, 5 competency, 5 research and development area. Well, first of all, you need some kind of physical embodiment, okay? So I'm going to call this aggregate, this team, body, let's say, right? Embodiment. In other words, this is the physical hardware, okay? It's also the physical interface with the world, okay? You can't move the Android if you don't have a body, right? And you can't say, when you have a computer program, you can't say, well, this is one program and this is another. But when you have 2 Android, certainly this one is Bob Android, this one is Alice Android. Okay, they're 2 different Android. There's a boundary. It's like an organism, right? It's an organism. Okay, so definitely, unless you are conjoined twin from birth, you are definitely an individual. Okay, you have your own experience, you have your own context, environment to navigate in. So this is the physical or embodiment. Now, in AI context, we have to also think in the general term, like the computational substrate, what kind of underlying computing platform we're talking about. Okay, that's one. Okay. Now, in the back of your mind, your objective is to make this Android very convincing, right? I don't mean convincing in a Turing test or imitation game where just a dialogue, right? The ChatGPT convinced you of that, right? But now you want a little human, right? A little human. But spare your thought a little bit. Human beings are not the only salient. It's called salient? Yeah, salient entities on this earth, right? You can have puppies, you can have cats or whatever, right? So let's think also, let's say a second division, you're making a dog or a cat or something like that, right? This, whether or not this capability extends, or if you start out with a company that makes a perfect Android, not Android, but a dogdoid AI, and you want to step up to humanoid AI, is it a big game? Is it a game changer, or is it just a little bit more compute? Okay, so a dog, same as a human, has to have a body, right? Right? Has to have a locomotion. So this physical embodiment from the dog department certainly, yeah, can generalize a little bit. Okay, so maybe dogs have 4, we have 2, but physical. So you need that. Okay, so that's the first aggregate of capabilities. The second aggregate of capabilities, first of all, is as an animal. Very simply, the animal is born, learn nothing about the world, but if you poke it real hard, it hurts. So there's a sense faculties for sensation, right? And there's So like internal evaluation. There's not that you have to, the dog is automatically born with a calibration of this temperature is too hot, this temperature is too cold, this is too hard, this is soft. So there's this feeling, right? About, yeah, this is good, this is bad. So there's some kind of like automatic scale of yes, no, good feeling, bad feeling. Okay? Good feeling, bad feeling. Dogs have that, so do we. So do we, right? So second facility, we'll call it, faculties for sensation, right? The third one, well, it wouldn't be AI if it doesn't recognize, object or whatever, right? The dog has to recognize the owner, first of all, it has to recognize that the thing moving toward it is a human being, okay? And then secondarily, that human being is somebody it knows or it doesn't know. So we'll call this cognition or recognition, right? Memory, recall, we put everything under this thing. Okay, so memory, we can call it memory, we can call it cognition, recognition. Dogs have that, so do we. So do we, right? So do we. Okay. Now, I'm going to skip to the last one, which is called the fifth one. I'm going to come back to the fourth one. The fifth one is called consciousness. Does dog have consciousness? Yes. Right? Dog have consciousness. It's aware of what it is right now. It's smelling. Okay. And if it's eating something, it's aware of the food. And if another dog comes and bites it, it's aware of that sensation. Okay. This thing is not, this thing, Android and human, we have to have that, right? And it's not that sort of like eerie, oh, does the computer, does the AI have self-consciousness, self-awareness, and it's going to have like a different desire from human being, and so in conflict, and then a few months later you get Skynet or something like that. Okay, that's about like sort of like this sense of self. Okay, emergent sense of self. I'm talking about literal consciousness. What's in front of you? What are you aware of? Okay, right now nobody is aware of. You're not aware of your breathing. It's automatic. Now that I mention it, you're aware of it. While you're aware, let's say, 1, 2, 3, let's be aware of your breath. Are you aware of what your right toe and left toe is doing? No. Okay. So I ask you now to be aware of those things at the same time. Can you do it? Well, this is a little bit deceptive. Neurologically, technically, you're not aware of two things simultaneously, but you switch back and forth so fast, it seems simultaneous. Okay, it's like people who say they multitask. Nobody really multitask, guys. Okay, if you're writing your essay and you're answering your email and then you're watching a TikTok, okay, and you think you're doing this simultaneously, you're not. You're just switching your attention back and forth. Okay. So this consciousness, this awareness of what it is at the forefront of your consciousness. That's common to dog. That's common to you. Now, how would this be common with an AI? Well, AI, okay, the intelligence itself, yes, let's say it's a robot, right? It has a motor sensor. It has a LiDAR. It has sort of like maybe a chemical sensor, okay? But at a given moment, to act on this or to bring it to the central compute, there's only one thing, right? So likewise, forget about this kind of distributed computing where you have this parallel matrix multiplication or whatever. But let's say in the central compute, right? The computer is looking at your input, what you ask. Let's look at it, various line of codes of the ChatGPT. There's gazillion lines of code, right? So what's actually the quote unquote forefront of the AI's mind? That's the consciousness, right? That's the consciousness. Okay. So what's the fourth thing? Well, the fourth thing is concept formation. Now, this is a little bit interesting. It's a little bit, and I don't want to dwell this on long. This is not a philosophy class. I'm going to maintain that this is really the game changer from a dog AI to what would it take to make a humanoid AI. Okay. What's concept formation? Well, precisely, I'm using pure language, which means absolutely nothing to somebody who doesn't speak English. And yet, through that abstraction, you have a picture in mind, internal representation of all the concepts, right? You wouldn't understand a single thing for the whole lecture if you were a puppy. Okay. Now, dogs can have all kinds of things analogous to human being. Okay. It can experience love. But a dog does not have an internal concept of love, right? So experience love. But while you experience love, you know, you're with your mom just made you delicious lunch, okay? And put your head down on her laps or something, and you say to yourself, this is love, or this is happiness, this is peace, this is home, okay? Dogs also have homes. They're very good at finding homes. There's stories of dogs that get, you know, go to different states and eventually find its way home. So for some reason, dogs have very good memory. So dogs knows what their home is, but the concept of home is where I belong doesn't have it. Doesn't have it. So I maintain, among other things, that of all the 5 faculties, 5 aggregates of capabilities, this thing really is a step change from, you know, animal kingdom in general to Homo sapien. We have ability, and from this we have all kinds of things. We have ability to form abstract thought, think in terms of mathematics. Animals are aware of numbers. They know that, you know, there's a lot of threat. There's 3 lions versus 2, but they don't have this concept of addition, multiplication, so, right? So anyway, my point right now is that of all these things, if you're really going to push AI, it's about creating this internal abstraction, this internal model, right? This internal model. So this is something that cannot, it's not automatic, right? The body is automatic. And in fact, you keep eating, you get bigger, it's automatic, so in a sense. Pain, and you might learn, there's a little bit of learning, so you can tolerate some pain as a good pain, like no pain, no gain when you go work in a gym. But essentially, your sense perception is, you know, you can still feel hot and cold, right? Likewise, this thing is automatic. If you see a picture of something a lot, you recognize, blah, 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 and this is always working, right? Your consciousness, you always have a central compute. But this thing here, though, which is a big game changer from dog to human, it's going to require a lot of learning post-birth, right? Because babies are not formed with the concept of love. They have happy, they enjoy warm milk, right? And automatically they can associate mom with warm milk, right? But the concept, oh, you know, this is not nice. I feel so safe when family or whatever. Okay, that's things like this. These are internal representation, internal model of reality. Okay, so it's a step change from, say, non-human AI. Okay. Now, if you recall, last week, I spent a great deal drilling the idea of 3 intelligence, meaning of intelligence, right? The first is AI, I meaning human-like. Second, things like business intelligence, military intelligence. I, intelligence means strategic or tactical information, right? That are of strategic and tactical value. And finally, computational intelligence, digital intelligence. This is about intelligent being, optimal solution, better solution than before, good solution, maybe the best ever, maybe if not the best ever, certainly better than your competitor's answer. Okay, better, competitive, you know, it's a good solution, optimal solution. And I maintain, okay, and you have to, I guess, you don't have to subscribe to my belief, but this is where AI pays a difference, right? Okay, having AI that is a lot more human-like but gives you stupid answer, that's old tricks, right? You don't want dumb chatbot anymore. We used to be fascinated with the chatbot, but if a chatbot gives you a dumb answer, we're not excited anymore, right? So it's about this intelligent solution. However, today I'm highlighting the difference. I'm almost picking on the different thing. I'm saying, hey, even though the ultimate games of AI is optimal solution, not human-like, the way to it is to exploit that humanness, that human form, that qualitative essence of human intelligence. Does that make sense? So now I'm going back to human-like as a definition of intelligence, except it's not as a criteria anymore. That, yeah, you sound like human, you sound like stupid human, good, perfect AI. Now, that's not what we want anymore. We want smart answer. However, in terms of AI research, development, and the next 20, 30 years that you're going to be knees deep in AI, it's about AI acquiring that essence of intelligence. Okay? This thing, this body, okay, people in robotics will be working on it. Yeah. And it gets better, by the way. There's this thing called soft robotics, which is even nicer than what we call hard robotics, like in the manufacturing plant. Okay. And this sensation is going to get better because we have scientific instrumentation. That's fine. This thing about cognition, this is good, right? CNN, convolutional neural network, can recognize faces, familiar friend, can even age you. Say if you simulate an age face, it's still going to recognize maybe as the same person. Okay, so, and that consciousness is the speed of compute, it's going to be there. But this thing here about ability to get AI to learn, that's really what makes the next generation or more advanced AI. Which comes to today's lecture. Okay, comes to today's lecture. That AI, it doesn't matter what form of AI, you open under the hood, there's always a machine learning engine in it. Okay, so that means that AI, when you open the box, there's always a hidden implicit machine learning algorithm. Okay, this machine, okay, I gave the game away by calling it machine learning, but as I have been trying to hint, right, the step change from, say, a dog imitating AI to human imitate AI qualitatively, okay, not just faster and better, but qualitatively, is this internal representation, this kind of ability to form concept, mental formation, mental construct. Okay, for the purpose of this class, I'm just going to call it thinking. Right? Again, with respect to the second facility, dogs can, maybe ever experience love. If you loop happiness a few times and association with caregiver, happy caregiver, loop it together, then dog experience love because this caregiver give me food, give me warmth, right? Experience that. But to jump from experiencing love to have an internal representation of a concept, hey, this is love, right? That's something that a dog android does not have to have because a dog doesn't have it. But a human android, a humanoid android would have to have it. So there has to be this kind of internal representation. And that internal representation is abstracted from what's out there. Okay. So it doesn't come from genetics. It comes from experience, right? Nurture, not nature. Okay. So today it's about how inside this, there's that. Okay. So let's lay out the groundwork. Okay. So let's go to the second slide, so to speak. I'm going to write 3 words. Okay. One is calculator. Okay. One is calculator. One is computer program. Okay. And one is an AI. I'm going to call it engine. It's a little bit vague at the moment, how I mean by that, but it's basically everything that, gets an AI going. Okay. Right. What is with calculator? What is with calculator? Come on. Okay, tool to solve mathematical operations. So that means that it can do this, f of x, and then gives you y. Right? Simple, right? Okay. X could be a number or two numbers, right? So exponential of 7, that's a number. You just supply with 7, but addition takes two numbers, right? A and B. You supply A and B, the function is add them together and you get A plus B, right? Okay. So think of this. I'm going to use a different word now. I'm going to call this I. I'm going to call this O. In other words, it's an input and output. Okay. Now, right now, okay, right now, the input output is based on, say, a calculator has 5 buttons. So there are actually 5 functions that you can do. Okay, 5 functions. In my go-to computational platform, Mathematica, maybe it has 5,000 built-in functions. But if all you do is use the built-in function, it's a calculator. It's a calculator, right? It's a calculator. Now, ChatGPT is not a calculator, or is it? Or is it? Let me ask you a question. Is ChatGPT a calculator? Well, when you open a session, you give an input, it gives you an output, right? Now, of course, there's a little bit more to that. There's a memory buffer, right? So it can remember the previous conversation, and that's just part of the programming. So there's some kind of loop, some kind of buffer. I don't want you to take any note right now. I want you to just, yeah, listen to me. So right now, ChatGPT is operating in an I/O mode. Think about it. It's not ChatGPT in this sense. It's like a calculator. It's pre-programmed. Okay, it's pre-programmed. A mechanical calculator by nature can only do a few things. You know, those old-fashioned cranking machine or a Chinese call it tablet thingy, right? A modern calculator can do add, subtract, and whatever. Scientific calculator can do 10. Maybe Mathematica can do 5,000, 10,000. ChatGPT also has a function. A function is to generate word. That's it. Read and generate word. So in a way, you know, ChatGPT, if you use it in that capacity, it's not even an AI engine yet. Okay, we'll get to where how it gets to be AI engine. Okay, I'm just making this statement, which is supposed to be surprising, I guess. Okay, so basically, it's an I/O with fixed selection of capability. Okay, in a way, that's like animal with instinct. Okay, you said, you know, animal, squirrel gather nuts in the fall. What's the input? Input is a temperature or atmosphere, or dog senses the rain is coming. Okay, so it's I/O. Okay, and if it's programmed, in other words, there's no user experiential update. It's a pre-train. Okay, so when I use the word pre-train in ChatGPT, the P, in a way, it's like a computer. Okay, think of computer. Think of your calculator as a massively powerful computer, except you only have a button that calls 4 functions: add, subtract, multiply, divide. Right? Same thing. ChatGPT can do that. Fine. So how does this get to be computer program? So that's an I/O, right? In a way, computer program is when you try to customize the task of a calculator. So maybe I program, my program is to find an average, okay, of your height and compared to your height. What is that? That's adding a whole bunch of height and then divide. Calculator. Adding a whole bunch, divide, calculator. Keep one number here, keep number there, divide, another calculator, right? So it's a string of operation. You can think of it as a series or sequence of step. Okay, sequence of step. Okay, that's what a computer program does. Now, I'm going to use another word, which is called algorithm. Okay, algorithm. Algorithm is slightly more elaborate concept than computer program. A computer program gives set of instruction, right? An algorithm, and please correct me if I'm wrong, it is still written in computer code. So it is set of instruction. However, it has an internal logic to it such that you do some kind of internal processing in finite number of steps. That program stops in finite number of steps. So if I open a calculator or maybe even mathematics, I just leave it running. Okay, that's not an algorithm, right? But if I say, do this job, and this job requires you to add, divide, add, divide, n. That loop, that complete execution, whether or not it requires internal loop, it's an algorithm. So the best thing to think of an algorithm is cooking. You have ingredients, you have processing, right? And you have finished product. Okay, cooking has to finish. Okay, it has to end up with something on the plate. So there's we talk about algorithmic convergence and all kind of stuff. The point is that there's a beginning, there's an end point, there's an input product, and input resource, and there's an output that you decide. Okay, and there's also like external evaluation that this is a bad, this one tastes terrible, this one tastes good. So implicitly, even though an algorithm can produce anything, there's always associated with it some kind of evaluator of the output. Okay, and that evaluator is generally used inside the algorithm to improve the outcome as well. So think of you guys seen those celebrity chef, or maybe not celebrity chef, but those chef thingy, right? Well, if they do a competition, that's it. The evaluation is external. It's the end. If you don't make it to the next stage, you're out. Well, if you actually work in a restaurant, it's different. You're a junior chef, you make a dish, you go to your head chef, the head chef critiques you on that, right? Comes back, you do iteration of it, okay? So maybe you can think of one loop of from beginning to end of one dish. Maybe you have an algorithm, a super algorithm that is a loop that involves the head chef giving you the critiques, so that by the end of 5, 6 different trials, you make the best dish, and then you send it to the customer, and then that's really external. Okay, fine. So there is some kind of sequence, some kind of termination point. So that's what an algorithm does. Okay, fine. Right. So let's go to what makes an AI engine. Okay. Now, let's do this. Let's think of you not know anything about ChatGPT. Okay. And I move you back to 1950s, and ask you what would the that's just like the birth of computing. A computer can do things like for loop, right? Do while, or if then, something like that, right? Iteration, okay? And I ask you to build an AI. The instinct AI in this sense, I going back to the imitation game, right? Give a input, output, input, output, right? You can imagine that AI engine looks like if then, okay? If the input is good morning, the output is good morning, how are you, right? Imagine this. This is how you build AI. Conceivably, can you build AI this way? how about conceivably? It's not a good word. How about theoretically? Theoretically, you can, if you have infinite line of codes, because you have to cover infinite possibilities of input, right? And if you want to talk about conversation that is sensitive to what was said before, it's not just an input, but input joined with the previous conversation. So it's, it takes infinite computer codes to write it. Okay, but is it doable? It's doable. It's doable. Well, not doable. It's doable in a theoretical sense. Okay, if you have infinite lines of code, you can do that. So they decided real quick that this is not doable. Okay. However, in some case, where would you make this doable? How would you make this doable? Come on. I'm not asking you to take note. I'm not asking you to think. How would you make this doable? You restrict the input, right? And so you restrict the application. For example, if the input are blood sugars and call it blood pressure, yeah, age, something like that, then you can sort of like do sort of imitation of a doctor. Okay, a doctor that hasn't really finished a degree, just basically just took and medicine 101 or something like that, right? So maybe a very first year medical student, his medical knowledge, right, can be done this way. You can program that because there's always an else. If this input, then this. If then this, then this. If it's some other input the medical student has no idea, the answer is go ask somebody else who knows. Go ask a real doctor, guys. Okay? So as long as you have that option, right? Anything else I don't know, just throw it out. Yeah, you can do. Okay? And in fact, that's why this first generation, we call it GoFi, good old-fashioned AI, is still relevant for very well-proven, precise job, like certain medical diagnostic, like a screening, pre-screening. Okay, these are if-then rule-based, basically. That's the word, rule-based. So yes. Okay, so yes. Now, let me ask you this. Is this an algorithm? Not really. It's just a computer program. It's just computer code. If the input is this, the output is that. Okay, there's no beginning, middle, or end. It's not an algorithm. So let me put another word on it just to make sure you remember. Okay, so there's this is I/O. There's a computer program that has a special word called algorithm. Okay, and then this thing is still an I/O, right? Still an I/O, right? It's not an algorithm. It's still just this. Okay. Maybe I'll take picture of this so I remember what I said. Okay, we save this. I'm not sure where it would go, right? So what I do is just periodically. Sometime I just yeah, I think you can save this, but it has to go to cloud or something, so I'm not quite sure. Okay, fine. So let's start something new. Okay. Okay, now that is the fun stuff. So what can you do? Right? Again, you're still in 1950s. You can't program all the if then, but you have this ambition of creating a machine that behaves like a human being. Okay? And then you say, well, I can't program it, but I want it to behave like a human. Can't program human-like, can't program human-like. And I said to you earlier, programming in a biological sense is equivalent to built-in instinct, right? Genetic kind of thing. Then you said, wait a minute. I want it to be the human-like, but humans are not programmed either. When you were born, your mom did not, hook you up to strings or electrodes and program. So your capability is growing. And the reason it's growing is because it starts from nothing. In fact, you start with less than dogs. Dogs have better instinct than you do. Okay? Dogs have better instinct. So in terms of pre-program, you are like a very crude calculator. Your dog is like a scientific calculator. It's born with so many functions built in. Animals can survive in the jungle. You can't. Okay? So animals are really scientific calculator, has so many functions, 20, 30 functions. You are like idiotic free calculator. Okay? Add, subtract, multiply, divide, maybe. Okay? Maybe just add. That's all you did. That's all you do. Okay? So you actually are nothing pre-programmed. How did you become so much better? Again, because you learn. In particular, go back to the very first thing I said in the first 15 minutes. You learn here. Concept formation. Okay? You learn through concept formation, and you learn, the thing that you learn becomes concept. This concept formation, when construct, by the way, I'll give you a Thai or Pali word for the 5 things. It's called รูป เวทนา สัญญา สังขาร วิญญาณ Okay? Incidentally, I got very deeply interested in Buddhism and artificial intelligence kind of like around the same time. Not around the same time in the sense that, I've always been a Buddhist, but to dig deeper. Again, I was dig deeper in that. I've always been in science, but to dig deeper in AI, dig deeper in Buddhism happens sort of like around the same time, sort of like my second year, third year in college. And it's through this identification of the 5 aggregates was the thing that sort of like knocked me over the head. So anyway, so the 5 aggregation does make sense in terms of creating a humanoid robot. Okay, in Buddhism, it's different end. Buddhism is to say that your sense of self is an artificial construct. You only have just 5 things. You don't have this 6th thing called soul. That's just a sort of like a looped emergent property or something like that. Anyway, but back to humanoid android. Okay, you want to build humanoid android. That you can do, that you can do, that you can do. This is necessary because you always have central computing, right? There's always something on the cache. It's called current instruction set. Basically, the particular line of code it's executing. Okay, computer has thousands of lines of code. They're not executed at the same time. Okay, think of it that way. So here, how can dogs don't learn? So obviously, concept formation is not their job. Humans can learn. There's one inherent capability that is human, and that's ability to develop or grow into a language naturally. And so language itself is a mental construct. And through language, you gain a vast body of knowledge, which are mental construct. Everything you know that makes you human and not puppy, in a way, if you're going to write them down, chances are it comes in the form of mental construct, idea, concept, relationship, understanding. Okay, so I'm going to bunch everything under thinking. Bunch everything. Okay, fine. So now we got this thing where a baby, okay, has very little pre-program. So somehow from here to here, adult. Okay. So as a baby, you have very limited I/O capability, right? Nothing. But now you can have a lot of I/O, right? So you have a large set. This is a tiny set, right? But you can only get there if you have an internal set of function. So now I'm going to equate mental formation with functions. I'll just call it function because in a way you require, everything is built on function, right? But it's not function in a strict mathematical sense. So from here to here, okay, you can't program it, but you need to get a lot of function in the end. Question, how do you get there? And same thing with AI. AI is different. Well, it's not that different, but this is your brain, right? Your brain is like an architecture, but how your brain gets programmed, the connectivity in your brain is different. Okay, so this is brain 0. This is brain adult. Okay, brain adult has the same architecture as a brain 0. Maybe, yeah, it's actually even less, by the way. I don't know if you know this. Okay, your brain is less complex than baby's brain in terms of connectivities, because the learning, part of the learning is not to build new connection, is to prune nonsense connection. So actually, if you count, I think I'm not, don't get me wrong, but in terms of counting active connectivities, you have less capability than babies, except the babies are random, so it's no good, right? Now, think of this picture. Think of this picture, right? Now, think of ChatGPT. Okay, ChatGPT. So I'm just gonna GT. Okay, GT, because G is generative, it just means it keeps input I/O. So this is kind of the I/O flavor. T is like a brain. It's a particular design of a brain. Okay. Now, the GPT that OpenAI came with is like a species of animal that has a particular structure of a brain. That brain doesn't look like what's in your head, but it looks like something that I'm going to call it T. Okay. So the journey from here to here, GPT. Okay. Pre-trained. And you hear this, that right now, this transformer, the GPT version 3, okay, has 175 billion parameter. Okay, that's a lot. By the way, how many do babies have parameters? Adults, human being, about trillions. 200 trillions? Yeah, I think it's something like 200 trillion or something. Okay, it's just order of trillion. Okay, so certainly, it's not as complicated as a human baby yet. But anyway, the point is, this is all random. Okay, this is all random. At some point, this thing becomes trained. All right, this thing becomes trained. It's called P because it's pre-trained. What it means is that it's already trained for you. Okay, so when you go to a ChatGPT, you don't go to a GT website and then supply your own text and then ask it to learn. It doesn't learn at all. Okay, you think it learned because you give some information about yourself, right? And it learns about you, right? Does that sound right? When you use ChatGPT in a long session, yeah, it's learning something about your preference. It's learning all that. It's not learning, guys. It's just accumulating a bootstrap set of data. So right now, in the beginning, it has nothing on you. You say hello, that's one word. Okay, this guy said hello. You say something else, say, I prefer blue, I don't like red. Okay, that blue, not red, becomes another input. So basically, it's not learning, it's just stacking prior information. And then when it gives a result after 10 hours of conversation, it looks, oh, this thing has learned a lot about me. No, actually, you just given yourself a lot of information. In fact, if you log off, you go to somebody else's account, it will have no idea who you are. Okay? Right, fine. So somehow this thing, and how did we do this? We do this through process called learning. Okay? Likewise, this thing, because it's a machine learning. The point is, this is very important. This thing, unlike your learning is fairly continuous. If I would say, is your learning an algorithm? In a way, it is algorithm, but it's not a finite algorithm in the nice sense of the word. It's not computer algorithm because you don't stop learning, okay? Whereas computer can stop learning. In fact, ChatGPT has stopped learning the day it was launched. Okay, the day it was launched, it stopped learning. Okay, well, not the day, but long before. So this here thing, unlike here, which is kind of like open algorithm, this is an algorithm via algorithm. Okay, so now we talk about machine learning algorithm. So what's the story? Story is you want something that behaves like human, acquires internal concept representation like human, but the thing that you have is a computer, so you want to program it, but you can't program it. But then you say, hey, human beings are not programmed either. So what is the flash of insight? What's the flash of insight? Flash of insight is, yes, you can program it, but you don't program it with the I/O response. You program with the ability to learn. Okay, that's it. That's the flash of insight that transformed AI from, you know, what would have been just a massive set of if-then that's only applicable to a very narrow area, like, you know, pre-screening for COVID or whatever, or, you know, college admission. That's an if-then rule. If your SAT score is above this, and if you blah 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 blah. So that's basically a bunch of rule-based if-then. What transformed rule-based, which would never work in 1,000 years because it would take infinite years to develop that code, into this, despite the fact that you can't program intelligence, is you can program learning, program ability to learn. Okay. Now, so in human biology, it's sort of like mixed. Okay. What you learn in life and you learn how to learn. In fact, I teach a course called lifelong learning. So, hey, you've been learning all your life. I'm teaching you how to learn. So in human being, it's very fluid, very organic. Okay. What is content? What is a process? What is F? What is X? What's, you know, it's all big mush in the sky, in the head, right? Whereas in computer, it's very clear. So what makes an AI engine? So if I were to go back to a picture that I don't have, okay, calculator, I/O, program, series of operation, okay, and then algorithm. What makes an AI engine is, okay, now watch this. This is magic happening, okay? The algorithm, right? The algorithm is a little bit like programming, except it sort of like has a finite point or something. I'm just gonna write it like this. Okay, so this is kind of like to denote the fact that, you know, anything goes, whatever. But an algorithm, yeah, there's a beginning to the end. Okay. What an AI engine is to have two blocks. An algorithm, this thing is what? F and O is what? It's a function, right? and an F. Okay, so this thing has an F. This thing, this program in itself, in a way, you can make it into an algorithm. This, okay, before I clutter up, I'll take the picture of this because it looks pretty. Okay. So it's not one shot, it's a two-shot thing. Okay. I can't program F. I can program algorithm. The trick is this. The algorithm is supposed to produce something, right? So let me write this function. So what is thing? Okay, this is a product of an algorithm. Let me ask you, what is this? What is in that algorithm? That algorithm is function blank to function finish. Okay, so now you're gonna say, what is a function blank? What's a function finish? Long story short, that's the function before training. That's a GT. It's just an architecture. It's a blank brain. It's a baby brain. It's a blank OpenAI creation. It's programmed in as a data structure and function and list of operation. And it has, like a baby brain, it has parameters. The value of that parameter is not tuned. So the algorithm, the job of the algorithm is to take an untuned function, end up with a tuned function. That's it. And in fact, that's how your brain works. Okay, of course, your neurons are regenerated, so you don't have the same neuron you were at birth. But think of it as, you know, that neuron, even though molecularly it's a different thing from when you were born, but you can think of it as the same neuron. But that neuron used to have crazy parameters, crazy connection. It doesn't know what to connect with. After learning, it knows to connect with this. And that's how you become an adult brain. Okay? That's becoming an adult brain. Why do I place so much emphasis on bachelor education? I may have told you that to give an analogy, okay? You are not pre-trained yet. Okay? Biologically, you only become pre-trained when your brain kind of like crystallize. So in a way, you are kind of like mid-training. Your brain is not crystallized yet. This thing called frontal, dorsolateral frontal cortex, which is kind of around here. That's the last area that's not yet crystallized. By the time you're about 25, it's crystallized. So you can think of your brain as at 25 as a pre-trained, not transformer, but you know. And every subsequent training from there is about stacking information set. Okay. Yes, there is research called neuroplasticity, which means your brain does emerge, you know, change over lifetime, but it's very limited. Again, anything biological is messy. There's no hard and fast, right? With a computer, you say, okay, this is my launch date for ChatGPT. There, I freeze the parameter. Well, in a human brain, you don't have a, you know, happy birthday on the 25th and then freeze your brain. But it's kind of like that process. That's why you have the best learning brain right now. Okay, because you're still in a training stage. Okay, when your brain freezes at around 25 again, give or take, everything is about stacking information, prior information set. But we still call that learning. I'm learning new things every day at my age. But you know, technically, I'm just feeding off of my accumulated database. Okay, just like ChatGPT over a session accumulate information about you. Over my lifetime, I accumulate information about how the world works. So yeah, I'm, you know, wiser than when I was, blah, blah. It's like I'm a longer session than you are, that's all. Okay? So use your last Dorsolateral prefrontal cortex days wisely. Wisely, okay? If you're gonna waste your brain doing some stupid things, do it maybe a bit later. Okay. So there it is. There it is. That's the name of the game. Okay. Okay, now you can take note. Okay. Now you can sort of like go a little bit passive and just write down what I say or whatever. Yeah. Okay. So that's sort of like the long arc of how is it that you build AI through machine learning algorithm, and the result of your building is basically big F. Okay, so large language model is a function. You are a function in a sense, right? Because I can ask you a question that's an X. You can give me an answer that's a Y, right? You can wake up and smell the air. That's an X. Okay, you realize, oh, it's late, or something smell funny, or something smell nice in the kitchen. Maybe there's food. That's Y. Okay, so you are basically big F. Okay, or set of F, if you like. Okay, but I just think of one big F. Okay, so let's get to the. Okay, so underline all that, right? Now, second part of the lecture, how? Right? How does machine learning algorithm works? Right? Well, this is kind of like self-reflective, right? Because if they're gonna take inspiration of programming computer, they try instead of programming a computer to have an intelligence, they program a computer with the ability to learn, right? And learn what? Learn internal concept, mental construct. Okay, สังขาร Okay. So how? Baby. Again, let's do that again. Baby. Okay. Baby. The only thing you were equipped with when you were born, number one, a little body. Number two, sense organ. Okay. That's it. You just got those two. Okay. And of course, you have a consciousness. So you have a central processing. You're processing your sensation. Okay. Now let's put 2 and 2 together. I sense with my nose smell. Okay. And I sense with my body soft touch. And a little bit later, I also sense nice feeling on my lips because I'm starting to feed. Nice feeling on my stomach because I'm full. Okay. So pretty soon I'm associating this thing together. Right? This thing then builds a cognition. Smell of mom equals food. Smell of mom equals nice. In fact, pretty soon it becomes smell of mom. Hey, that's the lady. And becomes concept of mom. Okay. And then you experience other thing. You have concept of human, but not mom, dad, blah, blah, blah. Okay. So that's very rudimentary, right? Now, how do we get to concept formation? Well, I recognize mom, I recognize dad, but this thing about mom is nice. Okay. Dad is loud or whatever. Okay. Or more importantly, when I see dad, I see mom. As opposed to when I see doctor, I see nurse. Okay. I see doctor, I see nurse. I don't get fed because I'm in the incubator or whatever. Okay. But when I hear the sound of dad, hey, I see mom also. And the nice feeling, everything now nice comes after it. This association, this coupling between concept of doctor with nurse and dad with mom, let's say, who taught that baby? None. All right. but the baby has an internal capacity to link things that appear short distance together. In this case, short distance usually means time. Okay? So the dad can be in front and the mom can be in the back. That's fine, as long as dad and mom appear sort of like within minutes of each other. So it's not distance in a physical space, because after all, baby can't sense beyond 2 meters. By the way, first baby up to 6 months, they can't see beyond here and there. Okay? So if you have a newborn and you go, hello, and it doesn't respond, don't take it personally. It can't even see you. Okay? But what they can sense is closeness in time. And there's an internal compute that associate two things that appear close together in time as a cluster, right? So baby now, from, let's say, dad, mom, doctor, nurse, okay, okay? This is my input, and this is appearance, okay? And what is actually my input? So I'm gonna index this with time. So appearance of dad, appearance of mom, okay? What's the output, guys? What do baby produce internally? What the baby produces is a partition of items, right? And this thing is by what function? Closeness in T. Okay? Closeness in T. Okay? If T of dad and T of mom are close together, yeah, they come together. That sort of thing, right? I'm obviously simplifying, oversimplifying all of this. But you guys get this, right? Now, to give you the, reveal, this process is not supervised. You can't control the baby because you can't, unless you shut the baby's eye and close his nose, turn off the sense organ, which is dangerous to do, so you don't. You just leave the sense organ running. So this detection of position, detection of presence, and the evaluation that this present is T and this present is T minus 2 seconds versus, something far apart. This is completely automatic, right? It's unsupervised. So I'm going to call this process unsupervised learning. Okay? Okay. And this process is probably the first learning you did as a baby. Okay? Because after all, you don't even have the power of language. Okay? You know how to identify dad and mom together, but you don't even know how to call it dada or mama. Okay, so that's it, right? So this is day one. Now, I'm going to go to a different mode of learning. However, let me interject here with a thing called concept of language. Okay, so I'm going to interject. So it's not, I'll come back to a second mode of learning, but let's call what's a language. Okay. Okay. Well, for the purpose of this class, nobody does this. I'm going to separate language into two classes, theoretical and empirical, or artificial and real. Okay. The theoretical language, what does it have to have? Think of Star Trek when they talk about Klingon or something, right? What's a language that Klingon speak? I don't know what it is. Like I did. Oh, it's called Klingon as well. Okay, it's like Thai people speak Thai. Okay, good, gotcha. Okay, so Klingon. right? A Klingon. Now, there are people out there who are such a big fan of the show that they learn how to speak Klingon, right? So what does that Klingon consist of? First of all, how do you show off you know a language? You know how to say things, right? So basically you have vocab and grammar. That's it. That's it. Why do you need grammar, by the way, guys? Why do you need grammar? Because in English, I kick dog is as different as dog kick I or me or whatever, right? Dog eats cat or dog chases cat or cat chases dog, right? It's positional, but you superimpose on that position in English, this guy does this guy to that guy. Okay? This actor, acty, action. Okay? In Spanish, maybe you start with action and with actor. So when you say that, you have to interpret different way. Now, this is very important. Bear this in mind. Okay? Bear this in mind. If I didn't tell you that in Spanish, me llamo, I call myself, that's my name is. Me, that's acty. Llamo is this, okay? Spanish, by the way, okay? So in English, I call myself. Okay, what I call myself is my name, basically, right? I call myself, right? In Spanish, it is me, and these two together, llamo. Myself, I call. Okay, myself, I call. Did you know that? You didn't. You have to learn this. You have to learn the grammar. Well, first of all, you have to learn the vocabulary, right? And the grammar. And otherwise, you can't operate in the language. Bear that in mind, okay? So it's very structured. It's got content. It's very structured. However, a real language is not like Klingon, because a real language has all of this and corpus. Okay? So let's it's not really a nice picture, but I'll take it anyway, just in case. Oh, maybe you can take. Okay. Okay. Right. So you have vocab, grammar, and corpus. What are corpus? Corpus is the body of expressed language. Think of Wikipedia. In English, it's an English corpus. Wikipedia in Thai is a Thai corpus. Implicit in that, it's just a bunch of letters. However, it uses the word vocabulary in the right order, grammar, to make sense, semantics. Okay? Now, again, let's go to babies. How did you learn? Okay, presumably most of you are Thai. How did you learn Thai? Did somebody teach you alphabet first and spelling and grammar? No, absolutely not, right? This is how baby learns. Baby learn. Let me write again. I don't know why my handwriting is so bad. Vocab, grammar, and corpus. Okay? This is how you learn. You as a baby. Okay? Okay? As you become a teenager or young adult, English. Now the process is different. The process, as you are bigger, and the bigger you are, the more you rely on this process. Right? Right? Now, obviously, you use a bit of both so that you learn English grammar, but then, you spend vacation abroad, you start talking, so you immerse yourself in the corpus, and that makes you very proficient. Yes, that enhances it, but you can't start with corpus. If I drop you off in Japan and you don't know how to speak Japanese, not a first thing, it's very hard for you to learn, right? In fact, if somebody's going to start learning, it's going to start by vocabulary, cat, dog, I, like you. Okay. So right away, it means I before you or whatever. Okay. So if you learn a second language, okay, you can do this. Okay. Now, anybody spot the theme? Anybody? Learning from vocabulary and grammar can be rule-based. Yeah? Yeah? Learning from corpus cannot. So you have to have innate ability. You have to have ability to learn. In fact, that's what learning algorithm will be doing. Okay. So there. Now bear in mind this is exactly what happens with anybody? Large language model. Right? How does large language model learn? It learns like a baby. In fact, all the languages, Thai, English, there's no native language in ChatGPT, guys. Well, technically that may not be true. There might be some, yeah, there might be some kind of like embedding structure where you embed the English language and then you map. So I take that back. But anyway, just a complete corpus absorption, to absorb a corpus in a language, it's pretty much learning as a baby. Yeah, it's learning as a baby. So this is you, this is adult you, this is a transformer you. Okay. Now what times it? Okay, bear with me a little bit, and then we'll take a break. I'll show you how things work, sort of like with your program. Yeah. So let's say now you have the power of language. Okay, I move you to a kindergarten. Okay. Before you are kindergarten, you learn by this absorption. You see adult picking up an apple and say this is an apple. You don't have to tell the baby this is called an apple, right? It's unsupervised. Okay. In fact, that's how baby give a nice surprise to their parents when they recognize things without being taught. Hey, how do you know that's a Volvo or whatever? Gets very impressed because, well, we talk about Volvo when there's a Volvo and the baby see a Volvo and Volvo. Okay. And I say, oh, wow, I didn't teach you that. How did you know? Right. The point is that only gets you so far. What if I want you to learn all the cars? What if I want you to learn all the vocabulary? I have to be more active in the learning process. That's where teaching comes in. And teaching in that strict sense of the word is a supervised process. Okay, how does supervised process in learning work, guys? How does supervised process in learning work? I show you this is a key. Okay, watch me. Yeah. So I'm teaching you now. This is a key. Okay. And then I say, what's this? If you say apple, I say wrong. Guys. Okay. If I show you this and you say apple, I say wrong. If I show you this and you say key, I say good. Good little Johnny. So my feedback is immediate. Okay. Remember that chef story I told you about? Well, you have to sort of like finish the whole dish before your head chef tells you if it's good or bad. With this, every single step, you crack an egg, good or bad, or take a soy sauce, good or bad. It's every single step. Okay. So this is kind of very closely supervised. Okay. So first, I show you this comma key. This comma key, that's a pair. Okay. What is that pair? It's an IO. It's the appearance of this comma with the word key. Right. And then I test you by doing this, and you have to generate the word key from your mouth. If you generate the wrong word, I say wrong. If you generate the right word, I say right. What else I do? Has Johnny really learned how to identify keys? So I say, Johnny, what's this? This is also keys, but different keys. That's the power of generalization, right? If the baby say key, good. If the baby say key, apple, no good, right? So the whole point about supervised learning is that there's a match pair between I and O, and there's a right or wrong about it. Okay. Now, that right or wrong is a Boolean statement. Yes, you said the right word, wrong, but sometimes it can be not strictly yes and no. It could be partial right. For example, I can say this, and you don't say key, you say car. Okay, that's partially right. Or you say wallet, but that's also partially right. But the main thing is key, because wallet is ubiquitous. You see it everywhere, but keys are very special, or whatever, right? So there's a right or wrong, but there's also a degree of rightness and wrongness. Okay, so it's not hard and fast necessarily. Okay, but essentially there's a feedback. So this process, unlike that language process where as a child you use one mode, as an adult you use another mode, this process, the minute you acquire language, you can use it forever. So I'm going to draw you as an adult. And what I give you is an X, Y pair. Okay, watch this, guys. Okay, it's a pairing of X and Y, and it's a set. That's my entire input. Now, pay attention to this. Pay attention to this. When I give a prompt, to ChatGPT, it's also a language. It's an I, but it's not a set of I, right? It's just that I that I use right now. Maybe it's a whole sentence, but it's just one I. Okay. This here, I'm giving a whole bunch. And through the magic of algorithm, what do I produce? What do I produce? Come on. It's only a few slides back. What does machine learning algorithm produce? It produces F. It produces F such that X, right? F of X. What's F of X? F of X is your approximation of Y. So I'm going to put Y with a little hat. Okay? Such that, again, there's a concept of closeness. Y hat close to Y for a whole bunch of them. Okay. So let me take a picture of that. Yeah, you did. I'll do this for just in case. Okay. Right. My input to an algorithm to a child is a pair of IO. Now, the algorithm here contains that correction thing, right? That Yes, Johnny, that's good. Bad, Johnny, that's not good. Okay. And the output of that is an F. F is the cognition function that you built to a child. That's the third aggregate, right? And this is also built over time so that when you were born as a baby, again, remember when you're born as a baby, you only have sensation. You only form concept of mom, right? Later. And then now you have not just concept of mom, you have concept of calculus, algebra, Archimedes, green function, stochastic calculus, all kinds of things can be taught to you. Okay, this is all acquired, but you know, you don't acquire just, this is what this is. This is what stochastic calculus. This looks like stochastic calculus. You actually understand the concept of stochastic calculus, right? So it's not enough for you to say, you know, I show you a bunch of letters, say, oh, that looks like Greek. That's cognition. But for you to actually read it and then, oh, it's saying life is good if you have been good to your neighbor or whatever in Greek. Oh, that's good. That's a good, nice concept. I'll apply it. I'll teach my children that. All this thinking comes later, this capability, right? But the idea is here. So you have this closeness that drives this. And so when you test in real world, you have that. Okay. This is completely supervised. This here, right here. Supervised learning. Okay, supervised learning. Okay. What's important about this? You are given designated set or pair. There's always I and O, I and O, right? Except, you know, it can be, O can be a word, O can be a number, O can be anything, okay? But it's always IO, okay, fine. Okay, that's it. Is that it? Is that all ability to learn? Okay, before I give you a break, there's one more. There's one more. There's one more. Okay. Okay. You are a student. Okay. One thing we notice is that when you go abroad for your junior year and you come back, you never show up late after you come back. Okay. So you kind of learn something there. Okay. Now, if you show up late and I say that's bad, that's immediate feedback, right? Maybe it works, but it works for this class because I say it's bad, right? But in other class, lecturers don't care, let's say. So you're late, you come in your pajamas or whatever with breakfast, they don't care. So it's not consistent. So it depends on how consistent the application is. And it's also like, it's not a general, okay? But let's say that you're in an environment where doesn't matter what the teacher is, the consequence is the same, right? When you come in late, you disrupt the class. I don't have to care. I don't have to say a word. You come in late, you disrupt the class. Your friends look at you funny. Okay? And generally, you know, when you go to junior abroad, you get a lot of stares. Except, you know, they might look down on you because you come from different country. They say, oh, what country are you from? You don't even know what time it is. Don't you have a watch where you came from? That sort of thing, right? This reinforcement doesn't happen immediately because you come in late when you go to school abroad and nobody stands up, okay? But they just look at you funny and you don't even know what that is, okay? And then you notice it's not about how you dress. If you dress the same thing, but you come in early, nobody looks at you funny. So over time, you have this kind of long evaluation loop. What is that evaluation loop? That evaluation loop is a long loop. And the input comprises of context. The context is the class starts at 9. It also has to do with you as a navigator of a body. I'm going to call the word, technically, it's called a state. Where you are, how fast you're walking, your heart rate, This is called state. This is state of who you are. Okay. Well, in this case, the relevant state is where you are at 9 o'clock, or what time it is you enter the classroom. That's also like a came from a state variable. Okay. So the context is the classroom. The state is you, and you navigate. So over time, this is behavioral. Okay. Now, college is a little bit long way to go. Let's backtrack a little bit. Actually, you know what? This starts very early. Okay. Now, I said as soon as you open your eyes and start to smell things, you have unsupervised learning process going. As soon as you have language, power of language, you have unsupervised learning. Okay. You also have this learning process the minute you interact with your peers. And that's usually kindergarten. In fact, it can start before that. But as a social animal, I'm going to use kindergarten as a starting point. Because at home, maybe you push something, it doesn't matter. You come to kindergarten, you push your friends, okay? You do this a few times. You take your friend's toys, or you bring a toy you don't share. 5-6 days, nobody likes you. Right? Now, notice, this process is very powerful because it gets reinforced by your peers. And for human being, peer is your environment. Okay? But that environment, this hostile look you get from your friends when you don't share the toys, can be physical environment. Okay? But for human being, usually it's social environment. So you are reinforced with good behavior. Okay? Now, if you push your friend, little Johnny push little Debbie, right? Now, over time, Johnny will learn that this is a bad behavior. Okay, but obviously, if I'm a kindergarten teacher, I can't stand by, right? So I would exert my supervised learning process. I would teach, Johnny, you don't do that. That becomes a supervised learning, right? But as you know, what's more important? What's more lasting? Telling Johnny, don't hit your friend or don't steal your friend's toy versus discovering that, hey, nobody's going to like me if I keep pushing my friends. Okay. So reinforcement learning tends to be, I would say, very powerful, I guess, long lasting. It's in the word. This is called reinforcement learning. You get reinforced positively, negatively. Okay. You get dirty look when you come in late. You get good look when you are alert and you know the answer and you can help your friends and you can explain your concept. Your friends are sort of like, oh, this. Over time, you know, somebody will become, hey, you know, this guy is a smart guy. When you when I go to class and I can't understand, I go to this guy. Nobody spells that out, right? But over time, this gets reinforced, right? And then you become like an important asset to your friends. Okay. So you win friends and influence or make enemies. This usually doesn't happen in the same way that you say, okay, this is bad, good, okay? Although sometimes we get that tribal, like, oh, this is from different school, you must hate them. That's stupid, right? But most of the time when you learn to like somebody or not like somebody, this is kind of like behavioral. And this loop is also automatic, but it's not completely unsupervised. It doesn't, it's not the same thing as unsupervised in that there's actually feedback, but the feedback is an accumulation over time, right? By the way, this is how you use AI in things like financial performance, because you know you can make profit and you can lose, but it's over time profit accumulation that matters. So reinforcement learning is sort of like the trick. So here, the diagram is going to look a little bit different. This is you. Okay. What's the input? Actually, you know what? This is what the input looks like. Environment. You. And your action. Okay. Okay. This is your input. Your input is an experience of environment, you, action, over time. And then you also have some kind of like evaluation function, response, over time. Okay. Now, why do I put this kind of bracket? Why don't I put a smile in here? Anybody? Because it's not immediate, right? It's sort of like a different set. So you don't push your friend and immediately get a dirty look. Sometimes you push your friend, you don't get a dirty look, right? Sometimes you come in late, nobody cares. But over time, there's a set of you plus environment or context plus your action, right? And there's a set of feedback, right? And it's not one-to-one, it's not immediate, but comes together. This is the whole body of knowledge that you accumulate. And just like any kind of learning algorithm, what do you produce? Anybody? You produce F. You always produce F. Okay? You always produce a function. Reinforcement learning also produces a function. What does that function do? That function do this. F environment. Now, this thing I'm gonna not call you, I'm gonna call state. Okay, it's a state of you. So this is kind of state of the environment or context or whatever. Environment, state of you, and action of you. Oh, sorry. Of you. Is action of you. Okay. Right. So your past action and what happened over time as you accumulate, you keep behaving this way and you get this feedback that's sort of like, it's not one-to-one, it's not immediate, but over time you can make a correlation between what you do and how people like you or do not like you, right? And over time, yeah, you learn the social function. This is a context. This is where I am. This is my action. The context is it's 8:55. The state is I'm downstairs. The action is run up. Make sure I get there by 9 o'clock. Okay. The state is, environment is, this is the market. My position is, well, I've actually bought a lot of things. And, you know, the market, I predict it's going to go bad. What's my action? I sell or whatever. I get out of that position before the market crash or whatever. Okay. So it's always producing some kind of action. Okay. Action. Right. And again, this is very, you know, for a machine, this loop is finite, right? But for a human being, this is forever loop. Like I said, you know, biologically, you are kind of like open-ended algorithm. So you're not a proper algorithm in the computer science sense. You don't have a terminal state. Okay, it's forever algorithm. So that's it. So that's what's called reinforcement learning. Now, I teach data analytics, right? In fact, today I'm supposed to get a published book from the printer, data analytics. It's interactive visualization, probabilistic modeling, and machine learning, you know, with Mathematica. Okay, that machine learning part of my data analytics course contains both supervised and unsupervised learning. It does not contain this thing, which is called reinforcement learning. Okay, sorry. reinforcement. And the reason for it, obviously, anybody? Why is it not part of my data analytics course? Well, because most of the time when you're working with data, you are generating some kind of insight or numerical insight like prediction, right? Predictive analytics, you heard of that word, but you're not producing an action. So where in a deep tech space, you would see the need to produce action? Robotics. Okay. So reinforcement learning is the most important. So if I were to say, okay, you're going to use AI, you're going to need machine learning. There are three principal paradigm. The word is paradigm of machine learning: supervised, unsupervised, and reinforcement. If you're, my job is to teach you data analytics, work with a lot of data, you become a data scientist. Chances are supervised learning and unsupervised machine learning. Okay, stick the word machine in there. Supervised machine learning, or just supervised learning for short. Unsupervised machine learning, or unsupervised learning for short. That's the relevant thing. But if I were to teach you a course in robotics, right? A robot has to say, where am I? Okay, the state is, there's a hot thing there, there's a hot thing there, there's an empty space there. My state is, I am here. The action is, yes, I can safely go here without bumping into things. Okay? Now, same information set, environment here, state here. If my action is to do this, I'm going to hit things, crash. Okay? So that's why this kind of action generation game is more relevant to robotics. Okay? So that's, you know, if you're going to take class in say robotics, that's pretty much the control mechanism you wanted to learn. Now, in robotics, you can go old school, just like in medical diagnostic, right? You can do if then. Well, in robotics, you can also do if then, because it's very reduced. Think of Roomba. You know what a Roomba is, right? A Roomba has is it lighter? Wait, basically, no, actually, it's just an infrared sensor or something. It just sends something and bounce back to say whether or not there's something in front. Okay, and that's it. Based on that, if then, if there's something in front, turn right, move. If there's something in front, turn right, move. So it's if then. So it doesn't have advanced reinforcement learning AI inside of Roomba. Okay, and Roomba is a very crude robot. Okay, but if you want to talk about autonomous driving, humanoid robot that makes a decision based on very complex set of context, set of state, set of tasks even, right? And there's another thing I haven't given you is the task, is the objective of the journey. That's actually in the state. You can think of a state as not only where you are, but how much reward have you earned, right? So that's also a state variable. Okay, so that's it. So in other words, from all this, you're gonna understand that underneath AI, it's machine learning, because all the capability, because what you want from AI is complex tasks, complex concept. That concept cannot be acquired through programming. It has to be applied through learning. And computer doesn't have inherent capability to learn. So you have to program it with a learning algorithm. A learning algorithm takes three forms, all inspired by human being: supervised learning, unsupervised learning, and reinforcement learning. Now, if you take a machine learning class, you would realize that the story doesn't stop there for two things. And this is very important. Maybe I'll put this on midterm. Why doesn't the story stop here? Number one, this machine learning paradigm, supervised, unsupervised, may be used in a different model building exercise, has nothing to do with AI. I'm not trying to build an AI, but I'm trying to build something else. Maybe logistic planning. Okay, so I don't really care about AI mimic human being intelligence, internal concept formation. I want it to do some task, but I use machine learning. So machine learning it's it's not, okay? And by the way, you might see this in YouTube or something. Don't believe them. Machine learning is not a subset of AI. In fact, there's a whole world, whole universe of machine learning that has nothing to do with AI aspiration. Yeah, the story may be that, yeah, machine learning is kind of motivated from AI programming or something like that. But no, AI has machine learning. Machine learning outside of AI is a huge area. So that's number one. The story doesn't stop. Okay. Now, yeah. Oops. สอนหนังสืออยู่ครับ Okay. So that's one point about the story doesn't stop. There's another point about story doesn't stop is that in the past 10 years, yeah, there has been an emergence of the fourth paradigm of machine learning that is not directly inspired by how baby learns or human being learns. Okay, you can say the first three are sort of like inspired by what human beings learn throughout life. The emerging fourth paradigm of learning is actually constructed within AI research. Originally to solve some problem, but now it's emerged as a fourth machine learning paradigm. I sometimes call it embedding learning. Sometimes you call it representation learning. There's no universal agreement yet on what it's called. But I think strong candidate. I would have used myself, by the way, I did a few years ago. This emerging trend, I would call it embedding learning. But I think nowadays the strong term for it is representation learning. Okay, and in a machine learning class, you see that. Okay, and that is a machine learning paradigm that is born inside AI world. Okay, so you can say that, yeah, there's some flavor of machine learning that doesn't live outside AI. Okay, not yet anyway. Who knows in the future? Okay, let's take a 5-10 minute breaks. Yeah, I don't have that much. Well, I do, but not much to necessarily plan for the show and tell. So take 5 minutes or 10 if you like. Okay. Okay, guys. So welcome to the second half of this class. So in the first half, which actually ran a bit long, we covered basically the underlying insight by which underneath every single AI engine you like to encounter, there is the engine underneath working under the hood is always something that invariably involve machine learning. Okay. Now, machine learning takes inspiration from human learning. And yes, human learning is not exactly an algorithm. If you want to call it open loop algorithm, it's continuous, right? But a proper algorithm, has a beginning, middle, end, that sort of thing. It has a loop. So let's talk about machine learning algorithm itself. Okay, so now we have machine learning algorithm. Okay, algorithm, right? Now, I mentioned to you already, right, that the best way to think about algorithm is to think of cooking recipe, right? A recipe. So you have ingredients, right? And ingredient is raw ingredient like a piece of chicken or whatever, right? And you have to process, right? So you have some very junior apprentice putting chicken in a little dice and whatever. So you prepare the ingredient, right? You heat the oven, you do this, and then you turn raw chicken into cooked chicken, but that cooked chicken doesn't taste like anything. So you turn bland cooked chicken into chicken that tastes good or whatever. Okay. At the end of the day, so you can think of cooking. Okay. Its ingredient. Okay. And then I'm just making one arrow, but it's actually a series of things, right? Okay. Right. In fact, dish is a good word because the end product is put on a dish. But if you go inside an elaborate kitchen, you see that they have plenty of dishes because intermediate input or intermediate output is also put on a dish, right? So you have raw chicken, you chop it up, you put on a dish. But that dish is not the final dish. So this thing about what's an input, what's an output, what's an input, what's an output, when do you call it a final input, output? It depends on the job, right? From that very junior apprentice point of view, his job is finished when he dices the chicken, okay? But from the point of view of the restaurant, right? The dish is not finished until it leaves the kitchen, okay? So, you know, this termination point, in a way, you have to understand that there's a possibility of nesting. Okay, that's a good word to learn. It's called nesting. Okay, so you nest little process inside the bigger process. All right. Fine. So cooking is a journey from here to there. Fine. Likewise, I maintain. Okay. And this is a crude way of thinking. Okay. Crude way of thinking. That F algorithm, okay, this thing is a journey from F theta 0 into F theta. Okay, now this means nothing to you right now. Means nothing to you right now. So we have to get a little bit mathematically. Okay, fine. So just take a quick shot of this, right? You know what? Okay, I don't think we have time for a computer demonstration today, but anyway, okay, right. Recall that in the beginning, in the first half of this lecture, right? I mentioned that a language has vocabulary and grammar and all that, right? Okay. So what's the analog in mathematics computational world of vocabulary? Well, it's basically named item, right? Right? So this is an apple. This is X. X is 5, whatever, right? So I'm going to tell you that there are, what do we name? Let's go. Okay, what do we name? We name entity. My mom. Okay, my mom. One entity, unique, individual. We also name concept, e.g., mother. Okay, again, this is very much, I mentioned mother a lot because I want you to think back that this is very fundamental human being. Okay, the very first thing, your very first human being that you interact with is your mom. So you name your mom. Okay, well, actually, from the beginning, from the first half of the class, you recognize your mom. You haven't even given her a name, right? Some of the babies don't even learn what the mother's name is until kindergarten, maybe. Okay. But the idea is you name entity, Bob, Alice, whatever. Concept, boy, girl, adult, children. Now, I want you to name number as well. Okay. We do name numbers. We do name numbers. Okay. Let me show you how we name numbers. We name number in one way. Anybody know this? Right? We name this number. Okay. This is a universal number. It's a ratio. In fact, an alien invader will know pi. Okay. Would not call it pi, but will know pi. So this concept, the right-hand side is universal. And so on Earth, this is known as pi. This is called universal constant. Okay. Universally, an alien doesn't call it pi, but what's universal is the concept of in two-dimensional plane, if you draw a circle, which is the constant distance from a point, and you divide by a segment that cuts through those points, the circle with the middle point, that's a ratio of 3.14. So this I will call constant. Okay, constant. Okay. Now, in computer programming, I'm going to say x is equal to 5. Is that a constant? That's a little bit tricky. As far as the computer knows, x is 5. X is 5, right? But actually, I can change it later. In fact, I change it all the time in my computer program. I may start out x equal to 5, and then x plus equal to 2. So that's x plus 5 plus 2 becomes 7. So it's a variable. Okay. So when I say x is a variable, what I want to do is to say x belongs to a real number line. You know what that is, right? It's any number between minus infinity to plus infinity. Normal computer doesn't have infinity. Mathematica does. It understands what computer infinity is. But so it can be anything. Now, don't confuse this with saying that x is the real line. X is not everything, but x can be anywhere on that line. That's what makes it variable, right? Changes all the time, like temperature, okay? So pi doesn't change, x changes. That's called variable. Okay. Finally, there's a third animal. This is the most important animal here. This animal is called, I'm just going to call generic parameter. Okay. That parameter is very tricky. It's not a constant. But for a given situation, it is. For example, a parameter that tells you this class start time is 9 o'clock. Is it going to change for the rest of the semester? Not. It's a constant. However, the same parameter for my afternoon class is 1 o'clock, right? So it's a parameter is something that can change, but for a given context, it does not change. Remember that? Okay. It's like I asked you a question, what's 3 times 2? You can say 6, right? And I ask another question, what's 5 times 2? It's 10, okay? Well, I can change the numbers, okay? So I can say plot a line y is equal to mx plus b, okay? Question 1, m equal to 5, b equal to 7. For the whole graph, m is equal to 5, b is equal to 7, right? For the second question, m is equal to 12, b is equal to minus 1. It's going to be 12 and minus 1 throughout the entire plot. So it's a constant that changes with context, like in the room. Okay, so this is very important. What do we name? We name these things. Okay, this is very important. Okay, what's that got to do with us? Oops. How comes the video? Okay, what's that got to do with us? What's that got to do with us? Okay, remember the objective of an AI, as we focus on, is to form some computational representation of a concept. And that concept is always expressed as a function, right? It's a function. So the whole purpose of machine learning is an algorithm that produces a function. Let's see what the function looks like. I'm going to give you one function. Y is equal to mx plus b, because you have seen this in grade school, right? In grade school. Okay. What's y? Y is a variable because y changes. What's x? X is a variable because x changes. Okay. X is not everywhere, but x can be anywhere. The point is, you give me any x, I'll give you any y. That y is determined by two things. The functional form, meaning what it looks like here. Okay, just look at my hand. Depends on this. And it depends. Now, if I just told you this, what does the line look like? You can imagine in your head it's a straight line. Why don't you imagine a curve? Because you know that with that shape function, you can't draw a curve. Okay? You can only draw a straight line. So in your head, you're thinking straight line. But which straight line? And that is where this guy comes in. So this is intercept, and this is the slope. Okay? Right? So if I'm going to form mental concept as represented by a function, I'm going to have to build an F. And AI is an F. And F is basically you think of it as mathematical function that takes input and based on operation. In this case, it's multiplication and addition. That's the operations. And M, the B, those are the value. That value is only a constant for that graph. So that value is a parameter. In other words, in this case, in this very simplistic case, this is a variable x, okay? F given theta is linear given M and B. By the way, I'm just going to write the right word for it. It's not linear, it's affine. Okay, but don't worry about it. Okay, technically, linear is not the right word, but for this class, I'm going to call it linear function. Okay, because it draws a line. It draws a line. Linear function given value of MB. So you specify two things. It's always a two-stage. A function specification is always a two-stage. Okay, and depending on what function, the specification that comes is different, right? It's like when you specify an option. If you're buying a car, you can option for color, engine, right? But you can option for flavor, okay? If you're specifying a dish, you can specify for what kind of meat, what kind of flavor, but you can't say, oh, I want a spaghetti with a V8. Means nothing. Well, actually, sorry, V8 is a tomato juice. I can't have spaghetti with a hybrid V6. Okay, means nothing. So when I say F given theta, it's actually theta given F. In other words, f is a function that does the operation. The actual operation depends on the value of the theta. However, the definition of theta depends on what f I chose, right? So if I did something else, I add kx squared to this. It becomes another function. And now it becomes quadratic and with a k in it. Okay, with a k in it. Okay, fine. Okay, fine. Sorry? Theta is my generic term for a parameter. Okay, just like I use f for function, x for variable, and y for output variable. I use theta for parameter. It's just a convention. Good point. Again, it's about context. How do you compute? Okay, so this is I'm going to write this as a full-fledged thing. Y is equal to f x given theta. Okay, remember this for the rest of your life. Now, to your question, what's the difference between x and theta? They're both input. However, one input is a constant for that job. You can't change theta. So once I say y is equal to 3x plus 4, I can't change 3. I can't change 4. I can only change x. Right? In that sense, parameter is like a placeholder. If I'm talking about this line here, f has two spots. It has a spot for the intercept. It has a spot for the slope. But once you occupy that spot with a number, you can't change your mind now. Okay? You can't keep plotting this line, m is equal to 5, and then all of a sudden m is equal to 7. No. Right? In the same line, you can change the x all you want, and then you get a change in the y, but you can't change the m and the b. Okay, let's watch this. Okay? Watch this. Okay, now remember this picture for the rest of your life as well. Since I wrote it so well, I'm going to take a picture of it. Okay? Your variable, when you go to ChatGPT, you can put in anything you like. You can change it, right? ChatGPT is a function. It's a large language model. And it's going to give you response. Okay? Now, what makes this a ChatGPT? Now, look at this, guys. This is advanced, like 2-3 lectures, but you might as well learn of it now. ChatGPT, well, its job is to chat. But the function itself is called GPT for a reason. For a reason. Number one, T is the name of this large language model. Just like the function can be linear, quadratic. My name, the name of the function that OpenAI created is called T for transformer. Okay? The G, generative. The way generative does is it simply means that if you want to generate response that has 3 words, what you do is generate the first word, put it in here, and generate the second. So it's kind of like a loop, self-generated. Okay, so that's kind of like it's very significant, but in this context, it's a detail. Okay, where does the word P come from? Pre-train. This is what happened, guys. This is what OpenAI did. Start with a T, given theta 0, meaning beginning. And that has 175 billion numbers. So it has 175 billion parameter, right? A regression that you did in high school or grade school has 2 parameters. Okay, that's a function. The function that OpenAI built is called T for transformer. That function has how many places to hold parameter? 175 billion. That 175 billion in the beginning is random. It's from training that ends up with the actual value. Once the training is done, this becomes T given theta. And that theta is fixed. So it is a parameter. If you took the same architecture as ChatGPT 3.5 and you ran it with a different data set, you get a different set of parameter. The reason it's called pre-trained is because once that parameter is fixed, 175 billion parameter is fixed, it doesn't change. That's what I mean by ChatGPT doesn't learn about you. It only stacks information about you so it can feed on it later. But there's no more learning. The I/O function is fixed when it's launched. Right? Very important, very important. It's fixed when it's launched. And this is called, the journey from here to here is machine learning. Now, another word for learning, if you want to say, yeah, you don't want to sort of like, is it learning? Is it teaching? Unsupervised is learning, but if it's supervised, it involves teaching, learning or teaching. Oh, how about reinforcement learning is by experience. So forget all that. Learning, teaching, let's call it training. Right? So training becomes a most general word, and it's also nicer because you apply it to this case. You just call it training. So that's why it's called pre-train. Untrained, train. Okay. The reason why do they call it pre-train, but don't they call it train transformer? Because in the old days, when somebody produces a model, they give you the model with empty placeholder. And you take that model home and you run it on your computer and then you train it. Okay. So you get a theta 0. The thing is, with ChatGPT, nobody in the world has the capacity to run the 775 billion. So, quote unquote, as a service, they pre-train it for you. So you get not just the T, it's a function and a placeholder for 175 billion parameter, but you actually get those parameters packaged for you. Now, of course, you don't actually get it. It's a cloud service, but you get the point. Okay. So this is essentially how. So let me rephrase. If this is data, okay, by data, I mean everything, life experience, machine learning. Okay, this is one representation, right? Representation. Another representation is to say that same thing here. Okay. So machine learning algorithm is a parameterization job. Now, in theory, if you're really smart, okay, part of this is create. You don't have idea what an F is. So you may do this. Okay, watch this. You may start like this. Okay, so you may build the function along the way. but most of the time, no. Okay. So you can think of it this way, right? If, okay, let me start again. I'm a PhD student. I'm doing research in AI. Okay. So for me, everything is game. I don't have to use transformer as my function. I can use radio basis function. I can use multi-layer perceptron. I can use this. I can invent my own function. So right now, my job as an AI researcher is this. Any function will do, any parameter will do. Okay. Now, as the world evolves, then you start to work with a fixed function with untrained. And finally, you get to F given theta, which is pre-trained, and that's the large language model. So this is kind of evolution of the industry as we speak. Okay. Okay. Now, I'm going to. I have a computer simulation to show you how this works, but let me do that next week because I'm going to take you through the process as well. So this whole lecture is talking. Never mind. Okay. Okay. Do that. Right. Okay. Commit this to your memory. Okay. But essentially, the job that you're going to learn about, even though right now you work in the world of ChatGPT, so you don't train anything, right? But you have to understand how it works. So it goes like that. So let's make machine learning algorithm as a journey from this to this. Okay, this to this. Now, imagine that you start a journey as raw chicken. One step is a diced chicken. One step is boiled chicken. One step is boiled and seasoned chicken. And one is boiled, seasoned, and garnished. Right? Okay. Just like that. An algorithm has steps. Okay, sometimes I call it loop because it's kind of similar step over and over. Okay, so the difference between a step and a loop is that a step can be fundamentally different. Like dicing is a step, boiling is a step. But if you think about dicing is a loop of chopping step. One chop is a step, two chop is a step, three chop is a step, right? Chop until it's diced. Okay, that's a loop. Okay, so loop and step in a way, you understand. So idea here is that you start from here, you go to here, you go to here, you go to here, and that's the final. Okay, that's the final stop. Okay, now unlike cooking, okay, where you seem to have finite step, sometimes you have this predetermined, right? So 5 steps to making a braised chicken something pasta. Okay, but think about chopping. How many times are you going to chop that chicken? Let's say you're not making a diced chicken, you make a lamb chop. Oh, no, the lamb chop is not. Literally, you're doing a mince meat, yeah, with hand. You don't know how many times you're going to stop, right? So the loop doesn't tell you how many times, but it does tell you the step. And it stops. It stops upon testing. If you see, oh, the meat is already meshed or whatever, you stop. Okay? So there are steps, iteration. The idea here is from here to here, how do you do it? Okay, now watch my hand carefully. The way it's done is theta I plus 1, start from theta I plus step size times direction. Okay, does that make sense here? Okay, now, because you can't do things in one shot, you have to do it in small steps. Okay. Let's take you on a journey. Okay. You are standing here. I asked you to go to the bottom of the hill. Okay. What do you do? Now, you see this, right? Where do you go? Well, you go here. Okay. You go here. However, unfortunately, you don't have that global vision. It's pitch dark. You don't have a map. You have no idea where you are. It's fog, whatever. But I asked you to go downhill. Your iteration, okay? Algorithm has iteration. Your iteration is as follow. Look at your feet. You can feel your feet, right? So even though you can't see a thing, you can feel if you're standing on a slope, okay? Go to the direction 1 meter in the direction that is downward. Can you do that? Now, that direction has to be reevaluated because when you go down, maybe you go down here, but then you turn left a little bit, right? So at every step, the direction changes. And you keep doing this. Now, this doesn't look like you're changing direction because you're going downhill. But imagine this is a hill like this, right? Sometimes you go down here, 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 here. Does that make sense? Okay. Any of you have been a Boy Scout? When you go to a elevation, right? The steepness, what's the word for steepness? Gradient, right? If you're a cyclist, yeah, you're going pretty fast, you're feeling good about yourself, and there's a hill coming up and it says 10% gradient. You're already sweating, guys. Okay, you and I, 5% gradient is just about what we can handle. Okay, 15% gradient, forget it. You're pretty much off your bike. So basically, it's a steepness. But that steepness doesn't give you direction because you're going along the road. Imagine the steepness that tells you the direction. Okay, so that's what the gradient is. And as you're going down, what's another word for going down? Descent. The machine learning algorithm is called gradient descent because how it gets from theta 0 to final theta is similar to how you walk downhill. So this is theta 0, and this is theta final. Now, notice, this is not what you want. You actually want here, but you never get there because if you're walking downhill, you never go uphill, right? So sometimes that is life. You get trapped, okay? That's not a big problem. I used to worry about that a lot when I was a PhD student. For one thing, we work with a smaller number of parameters, so they have to be really optimized. But with 175 billion parameters, yeah, some of them can be suboptimal and they still do a pretty good job, okay? That's not really technically accurate, but that's a story, but you can go there, okay? So this thing here, this direction is called gradient. And I might as well use the inverted triangle, okay? Now that gradient, in this case, it depends on the mountain, right? In machine learning case, what does it depend on? Well, I'm moving the function, right? So sometimes you call it gradient of f with respect to theta. I mean, symbol may change a little bit, but okay, something like that. Okay. So now you have theta I plus 1 equal to theta I plus step size times gradient of f evaluated theta I. Okay. Yeah. And you keep doing this. Okay. Now, the final point, and unfortunately, I can only make one more point, is that how do I do the gradient? That depends on the mountain, right? the way I do the gradient in machine learning is to say, if you're doing a good job, as in key, okay, means you're not making error. If you say apple, that's an error. So I'm going to make a hill of error. And the job of the baby is to minimize error. It's to go down the hill of errors, right? In time, I'm going to substitute the word cost for error because sometimes this is supervised learning, so there's right or wrong. But unsupervised learning, there's no right or wrong. So there's no error per se, but let's call it something you want to minimize. And what do you want to minimize? Well, you should minimize your ego, but really what you want to minimize is cost, right? So instead of using the word error, I'm going to use the word cost. So this is a hill called cost. Now, I did something that you should not like, which is I use F over here. This F is not the F that I was talking about. This F is a function that gives you the feedback. Okay, look here, guys. This F is not the F that you end up with. This F is a feedback function. So I'm going to change it. I'm going to call it an error function, big E. Okay, it is a function, but it's another function. It's not a function you end up with. It's a function that evaluates how well you did. So it's an error function or cost function. Okay, so maybe I use the word C, but you know. So anyway, so this is kind of like a funny F. Let's call it a funny F that stands for something bad. And this is the hill. So that's the hill. You want to go down this hill, unhappy hill. Okay, that's it. That's what machine learning is all about. In other words, every time you build an AI, you're trying to mimic the human being's mental concept. That mental concept is about prediction. That mental concept is about generating the next word. That mental concept is about giving the appropriate response to a prompt. Okay, and that can only happen if you have an internal representation of what works in reality. That cannot be programmed. So you have to program the computer instead to learn from experience. In the case of large language model, the experience is the very corpus. But in some other data context, the experience may be time series, past history of stock prices. That's experience. Okay. The point is, in all of AI, you only end up with the final F that represents AI if you perform this step. So that F has parameters. That parameter has to be tuned with respect to the data or the experience. And how does it do that? It does that by making small step. And how is that step guided? It's guided by the slope. The slope of what? The slope of the cost function. This is, well, I wouldn't say forever, but for the next 20 years, this picture will not change. Okay. Now, this, heavy duty researcher, they have advanced techniques. So sometimes they go jump over and get to the better one. There are all kinds of tweaks. Okay. In my PhD thesis, I didn't even use this thing. I used kind of like evolutionary search, but that's another story. But the point is, this is the mainstream. This is the benchmark. This is the best practice. This is the next 20 years of your life. Okay. This picture was not always like this. When I was your age, this was one of the picture. not all the picture. It turns out that this picture emerges as the way to do this. Gradient descent, okay? When I was your age, gradient, it was not taken for granted that gradient descent was going to win the world. It now is, okay? It now is. This is proven by success, okay? Sorry? Yes, the objective function here is the cost, not the f itself. Now, final function. Now, how do I define this? How do I define this? Well, that depends. For supervised learning, that funny, unhappy function is equal to the difference between your AI's output and the real output, which is y squared, something like this, okay? This is just one example. So this is the real input, okay? This is the real output. This here is your output, so it's y hat. How different it is, take the square, sum it all up, that becomes an error or cost function, okay? Now for unsupervised learning, is something else. For reinforcement learning, is something else, okay? The point is, you have to define that hill, and you have to go down. No, the cost function is based on y, right? And y is based on f. And f is based on your parameter. Okay, so let me go to the final picture, and this is the last picture for the day. You choose f from set of f. Okay, and that f then has theta. Okay, and based on this, you get some kind of output. And then the set of output tells you whether or not you're good or bad. So what you do is you try to move here so that the output good, bad. And by good or bad, it means how far down you are. Okay, that's a final picture. You can. The reason you don't do it is because this cost function is not the traditional cost function in the sense that you're minimizing logistic or something. That one, the variable have real meaning. The constraint have real meaning. But in this case, the thing that you are changing are 175 billion parameters. They have no real world meaning. They only have meaning with respect to the T function that OpenAI uses. So other than quote unquote, technically it's called regularization purpose, you don't put any constraint on it. Regularization in mathematics just means just make sure the number you end up don't blow up or don't do something strange, okay? It's called regularization, but that's advanced for you, okay? The idea is that these parameters like M and B, when you do a linear regression, can you interpret what B is? B is in absence of X, Y will have that value anyway. What's M? What's the M, guys? M is for every increase in X, you increase MX. For every decrease in X, you also decrease by that amount. You have a nice interpretation, yeah? You don't have nice interpretation about 175 billion parameters. And that's the tough thing about AI machine learning. You can't exactly explain. And that's what they mean by black box. It's not really a black box. It's just that you cannot assign human feeling or interpretation to any one of the 175 billion. Okay. By the way, when I was your age, it wasn't 175 billion. It was like 1,000. Okay. So it's very shallow. And the deep is, you see how it works. When we come back in 2 weeks' time, literally, I'll show you under the hood. Okay. I'll start with something like this, but in an algorithmic way. And I'll show you in a computer. I have animation. In fact, yesterday's class, I did show the animation because I skipped over some of the steps, but I'm glad today I didn't skip a lot of explanation. I elaborated on that. So that means we didn't get to the demo, you know, animation, but in 2 weeks' time, you see that. Okay. So with that, enjoy your class. I hope today has been a thinking day. There's not a lot of note to take, but you know, make sure you reflect on the inner conversation. Yes. Okay, good question. Good question. He asks, in this case, is optimization, in this case, is going downhill. It's also called supervised learning somewhere else. Actually, yes. In any kind of machine learning, if you have supervised learning, if your job is to predict y given an x, it's supervised learning. And supervised learning is always going downhill with the error. Okay. Now, the universal thing is, if you define anything as a cause, it's more general than that. And so this step of this thing was not invented. This going downhill was not invented by AI researcher. You know who invented it? When it was invented? 300 years ago, way before AI. This gradient descent is about minimizing cost of any kind. And that has been around for 300 years. It's been around pretty much, not the moment, but a few years after calculus was invented. Because calculus, okay, watch it. Last word, guys, pay attention. Calculus gave you that gradient. The minute you have gradient from calculus, you can do gradient descent. So this kind of minimization has been around way beyond. But it's not supervised learning because it's not applied to supervised learning algorithm to train a neural network, an AI, say, right? So yeah, in a different context, has not to do with learning. Again, minimizing logistic costs, that's got nothing to do with learning, right? So optimization is the biggest picture. Yeah. Okay, with that, I think that's a good dramatic stop. Okay, I'll see you guys in 2 weeks.